Hi, this is continuation for Power Electronics lectures where we cover the basics of power electronics, switches and topologies. So in the previous videos we have covered a video about buck converter, its analysis and design and consideration, and also we followed that by a video about boost converter. So we got the topology and we just mentioned two rules to get the relation between the input and the output. The first rule is to analyze our circuit in the on time and off time, and then use the voltage sec balance rule and capacitor charge balance rule just to combine these two circuits and get the final steady state values. The steady state values just explain to us how the current and voltage will be at steady state. But for the transients, we need to model it, but it's not part of this module. So I think in this video, we are going to start looking at new topology, which is buck boost converter, which is a step up and step down converter, and we have this topology. Again, what we note here, I think we have switch and inductor and a diode. It's the same as what the buck and boost converter contain, but maybe the places are swapped together. So again, to know and to understand what's the relation between the V input and V output, I think we need to go through the on time and off time circuit analysis, and then we average these by using the voltage sec balance and capacitor charge balance if it's needed. And before analyzing this circuit, we have again that switch, which is high side switch. That means it needs high side driver that we apply PWM on the gate here. And another important note, which is the V output polarity. If we have V input here, the positive there and negative there, the output will be inverse or has a reverse polarity. The negative will be on the top terminal and the positive will be at the bottom terminal here. And we will explain why from the analysis in the coming slide. So now let's start with two circuits, and we will take the first one and analyze it in the on time, and the second one and we analyze it in the off time. So during the on time, and what I mean by on time, switching on this switch. And by turning on that switch, that means we can convert it as a short circuit because we assume here idle switches. So this is the switch. What will happen to the diode? I think we have here the V input, and that V input will be traveling to that node, and that node is the cathode of that diode. The anode has a negative voltage there, so that's why we can assume the diode here is off. And after knowing the status of these switches, I think we can assume the current flow now. And I think the current will flow from the input there, going through the inductor, charging that inductor. So now we will assume that the current will be rising and going back to the battery. What will happen to the output? The output now will rely on the capacity charges to supply the current, and it will be in that direction. So this is the on-time circuit. And we want to ask the question, what is the inductor voltage? Because we want the inductor voltage in the on time and inductor voltage in the off time, and then we combine them together by averaging and equal it to 0. So now what is the voltage value here? We know that voltage there, that node here is the same as V input, and that node is 0. So the VL equals V input minus 0. Now go back to the off time circuit, and I mean by off time, that means this switch is off, okay, and we can just delete it. And what is the status for this diode? I think the inductor here will keep passing that current and pushing it to in the same direction there, but it has no flow through that direction because there is no way to reverse back. So that's why it has to go to that direction. That's why it goes through the resistor, output resistor, making the polarity like this, voltage there and negative there, and also charging the capacitor in that way, which is the reverse way, okay? So that's why the polarity here is reverse. So after passing through the capacitor and resistor, it will go to the diode and will forward bias it, converting it to like a short circuit. So we have on state for the diode and off state for the switch. I think the current will go from the inductor through the capacitor and resistor and going through the diode. I think the diode current here and the inductor current will equal each other in the off time. Okay, so keep that in mind. Now again, what is the voltage across the off time? I think that voltage node here equals the negative of V out, which is minus V out, okay? And that node will equal 0. So it's minus V out minus 0. So this is the value of VL during the on time, and this is the value of VL during the off time. What's the next step? You know, we use the voltage sake balance to average these values during the on time and off time, and by using the integration, during the on time we have this value, and during the off time we have that value, and we can get finally the relation of V output equals delta divided by 1 minus delta multiplied by Vn. And again, this is the steady state relation. And remember, I didn't put here a minus, but remember it's a negative. Why I didn't put here a minus? Because we assign the positive there and negative there. So it's a positive if we consider the polarity like this. But if we consider the polarity at the opposite side, so positive there and negative there, we should put a minus. Okay. So remember, the V output always has a reverse polarity compared with the input here. Okay, that's why I have this big note, and you can really get the minus here if you consider positive there and negative there. What is the relation between input current and output current? If we have the output current in that direction, so we can assume that the power input equals the power output. Power input is the Vn times In, and power output V output times I output. And I know Vn and In relation, so I can get I output and In relation by the reciprocal of the relation here. Okay, so I output will equal 1 minus delta divided by delta. Keep this as well in mind. And as we done in the buck and boost converter, we are going to see the waveforms of each component here. I think we have I input here. There's current, which is the same as the transistor current. We have IL here. In the on time, it will charge through the transistor here. And then after the transistor getting off, it will discharge going to the capacitor and resistor and going through the ID. So I assume that the inductor has the charging and discharging pattern, as we know always, and it should be balanced over the full cycle. And the voltage across the inductor here has a value positive, negative, and is computed in the previous slide. And when we look at the input current here, or the switch current, because the input current and the switch current are the same, okay? So it will equal the inductor current exactly, which is this part here, okay, when the switch is on. And it will be off during the off time of the switch. That means I have this portion there, copied there, which is the input current or switch current, and 0. Okay, and it has the value there and 0. So this is the input current, and it's the same as the buck converter current, input current, because we have the same situation where the switch is in series with the battery here, with the voltage source, and that means the input current from the voltage source is discontinuous. It's not continuous like the boost converter. Okay, so during the off time, I think that current will go through these components and then the diode. So if I am looking at the current through that diode, I will see the second portion of the inductor like that, and both of these currents now will form to me the inductor current here. What about the capacitor current? I think the capacitor always will pass the AC component of the current coming from that side, and that current here is the same as the current of the diode, so actually is the same as this waveform, but the AC component of that one. So the current coming out from that side, it's already supplied by the resistor and capacitor, the AC component from here and DC component from here. So if I assume the output current coming from there is steady like that, which is the average current here, I can subtract it from that waveform and I can get this waveform. So the AC component of that waveform is this. Subtracted from that the DC component, which is coming through going through the resistor value. And again and always, we know the waveform shape because we can calculate the average current and RMS current, and that helps us to calculate the power dissipation. So now let's go to analyze the circuit more and see what is the inductor ripple value. So we have the inductor waveform like that, and it's going from minimum to maximum, maximum to minimum. And from minimum to maximum, during the on time, and from maximum to minimum during the off time. So I know in the on time VL equal Vn, but I know as well VL equal L di by dt. Di is the change in current, and the change happens, from minimum to maximum. So I can use that equation now, but delta IL will be replaced by this one, okay? And during the delta t from that time to that time is the on time, which is delta t here, okay? So that ripple happened during the on time, which is this time, and that equals V input, okay, divided by L. So I can use that equation to get the result of delta IL. But also I can use that part here. I can say that the ripple is IL maximum minus IL minimum, okay, and that happened during 1 minus delta t, okay, and by using the same equation I can say delta IL, which is delta IL here, okay, it happened during 1 minus delta t, and the value of VL, it was minus V output divided by L, okay. So I can use that equation or that equation, and finally I can get delta IL. It's the same equation as the boost converter, and we can reduce IL by changing the value of L or changing the value of the frequency. And if I want to design my inductor value, if I want to maintain the ripple within some values, maybe 1% or 2%, so I can really choose my inductor value to satisfy the requirement. Now, if we have that current going there, and that IC is rippling between positive and negative, sometimes it's charging and discharging, so I think there is some ripple also across the capacitor, and because of that current here going through that capacitor, I think that will result a ripple of the voltage across that capacitor like this, okay. So during the on time here, the current will go through the inductor, okay, and the capacitor will be discharging. That's why it's negative, okay, discharging and supplying the current to the resistor here, okay. So that's why we assume the current is constant always, because it has a supply during the on time and off time. So if we have that current leaving that capacitor, that means it's in negative, and during the off time the current will go and come from the inductor and charging that capacitor in that portion. So to know the ripple, I think we know the equation of the voltage across the capacitor equals the charges divided by the capacitance. But what is the charge? The charge is related to the current we are pushing or taking out of the inductor. At that time we have some charges here and they are coming out of the capacitor, and at that time we have some charges here and they are coming into the capacitor. But we know the inductor waveform, but what about the charges? I think the charge is the in the integration of the capacitor inductor, and the integration means here the area under this curve. And I think because it's a rectangle, it's very easy. The distance between there and there, it's I output. The distance between that point and that point is delta t, and that's why this is the area. Delta t multiplied by I output, and I can use that equation just to compute delta V output, which is delta I output divided by FC. So if we increase the frequency or increase the capacitance, we will get lower ripple at the output. And as we done in the buck and boost converter, we want to know the impact of I output on the IL, and if that will drive us to discontinuous conduction mode or no. So I think if I output has a significant value, because it's related indirectly to IL, it doesn't equal IL exactly, and IL doesn't equal I input exactly, because they equal each other in just the on time period or off time period. But the value of I output, the average value, will affect IL. So if I output is high, it will keep it in the conduction, a continuous conduction mode, and if it's lower a little bit, it lowers the IL, but it doesn't affect the ripple, and it will keep going down until we find the boundary condition, and then we'll go to discontinuous conduction mode. And that discontinuous conduction mode means that the off time here we cross the zero, okay, and keep at the zero for some time. But for the boundary, we cross the zero exactly, but we don't actually conduct during the zero time. And here we have practical waveforms of the continuous and discontinuous conduction mode, where we have here 10 volt as input and I output is 1 ampere, okay, but the inductance is 10 microhenry, where here we have inductance of 3.3 microhenry, okay. If we use the high inductance like this, so we are in the continuous conduction mode and the output current is the same there and there. But if we lower the inductance, we might go to the discontinuous conduction mode, and it happened. I think we explained in the buck converter why we have this ringing here, because of the parasitic capacitance and the inductance in the circuit. They start resonate, and we have the zero duration there, where we have the discontinuous conduction happen. So we have a question: what is the minimum inductance I need to make myself in the continuous conduction mode? If, for example, I'm working at 1 ampere, what is the minimum inductance? So to answer this question, we have to start from the equation delta IL equals delta Vn divided by FL. And if we are looking here at the rebel, and as before, we want this minimum value to be exactly 0, and that will give us the boundary condition and the minimum value of inductance. But how I relate that rebel to the IL value, or I output, or I input? I think that rebel here will go from minimum to maximum, and the average value of the current of the inductor current will be in the middle here, and I can say that the inductor rebel will equal double of IL, or IL will equal halfway between maximum and minimum, which is the rebel current delta IL. So I can say delta IL here equals 2 IL average. But the challenge here, what is IL average? Does it equal I output? Does it equal I input? Let's see. The average current here, okay, will equal I input during the on time only, okay? And during the off time, it equals I output, okay? So it doesn't equal I input all the time, and it doesn't equal I output all the time. So I can just relate it to the input current or output current during the on time or off time. So I have chosen to relate I output and IL during the off time, which is 1 minus delta. So the average output current will equal the average current of the inductor during the off time. Okay, so that's why it's multiplied by the off time. So now I have relation between IL and I output. I can replace that one with this relation, and I can get the minimum inductance value for that output current. If I want to keep my my converter to work at continuous conduction mode all the time, if I supplying, for example, 1 ampere or half ampere or 100 milliampere, I have just to assume it here, and I can compute that L. That L now will make sure that if I supply now 1 ampere, I will be in the continuous conduction mode. But I should know that if my current gone below that, so my inductance will not be able to maintain that continuous conduction mode, and it will go to discontinuous conduction mode. So this is now the value of the inductance, and it's similar to the boost converter, by the way. And if you don't want it by knowing the value of I output and V input, you can really change V input to V output by the relation, and also I output and V output to the resistance, and you can get this value. So this is another equation, but in terms of the output resistance, not the output current and V input. And again, we have the V output and V input relation in the continuous conduction mode. Is it valid in the discontinuous conduction mode? The answer is no, and we have to derive again, and the equation for the V output and V input is this one. Again, we have here negative because it's minus, and you can remove that one if you consider different polarity, but it has nonlinear relation with the V input here because we have a square as always before, and we have also I output. That means it's load dependent. And again, as we mentioned in the boost converter, that we have this relation between V input and V output. But if I have here delta, which is approaching to 1, so that term here will be close to 0. That means the gain will be very high. In the ideal case, yes, I will get very high voltage if I have delta approaching to 1. But the problem practically this doesn't happen because of the parasitic inductance and capacitance, and that will give us a limitation. In the practical situation, we have some limitation. We lose the efficiency and we lose also the voltage. That's why we limit ourselves to be within 70% of the duty cycle, and we don't go further because it's not really efficient. And again, we have a question. Is there any other topologies that make buck and boost converter? I think yes, we have other topologies, and two popular topologies. They are the Cook converter and CPIC converter. The Cook converter is exactly the same as the buck boost converter. It has a reverse polarity here because the gain is negative here, okay, and it works as a buck and as a boost as well, and the relation is the same, but it depends on the capacitor to switch the voltage across that capacitor, and that will make the bucking or boosting. We have another converter, which is the CPIC. CPIC has solved the polarity problem, okay, and now it has a positive gain. Instead of having negative voltage, we have here a positive voltage, and that one is another popular converter, and the relation is quite the same as buck boost converter. So we have different also converters with different arrangement of inductors, but we have here more inductors than before. We have two inductors here than compared with the buck boost converter, but maybe more efficiency and good performance, and they are really used in the industry. So I will not go into details of the derivation of these relations, because now you know how to derive it, and if you go through the same steps, you will get these relations very easy. But also the question again, is there any other topologies in the literature for buck and buck boost converter? I think we have many, but they categorize them in two groups. The first group is called the non-isolated converters. I mean by non-isolated, I mean like the buck boost converter, where we have the input and the output have common line or common ground here, okay? So the input and the output have reference, and that reference is shared by them. So that's why they call them non-isolated. So they are sharing that point. And we have conventional DC converter from that group, and we have interleaved this DC converter. What I mean by interleaved, for this example, instead of using one inductor, they use parallel inductors with parallel switches. So that will help them to reduce the ripple, okay, and make also the input current continuous more. And also I have the multi-port converter, where I have more than one output. I have another capacitor and another load. And on the other side, we have isolated converters, where we have the input side is electrically isolated from the output side, and that's done by the transformer. And these transformers are high frequency transformers. They are smaller compared with the low frequency and 50 Hz transformers. And this is one of the most popular converter, isolated converter, which is the flyback converter. So it has a transformer here, and it has one switch, and that is able to make step down and step up as well, according to the ratio of turns of that transformer. And that switch has to pulsate the input primary side here just to make the current alternating, and that can be really amplified at the secondary side and rectified here to get the DC current again. So it's like DC to AC to DC again, okay? And that one is very, very popular. There is another similar one, which is the forward. It's very similar to the flyback, but it has some small differences. One of another popular converter, which is the push-pull. Again, we have transformer that uses two transistors, and each one is pulling and pushing one of the inductor sides to make variable voltage and variable current that is alternating, and that's transferred to the secondary side and also rectified to convert it to DC again. So it's DC to AC to DC again. And we have Z source converter, and we have also full bridge and half bridge isolated converters. And this is an example where we have at the primary side, we have full bridge here. The full bridge means we have 4 switches, and they are like inverter. If you remember the inverter, yes, we have the inverter that's making alternating current across that inductor, which is the primary side, and that will be transferred to the secondary side by stepping up or stepping down according to the ratio here, and you can rectify it and get the DC again. So DC, AC, DC. Each one of these has some advantages and disadvantages and complexity and switch number of switches and inductors and capacitors varies between them, and the literature is rich of information about all of them, but all of this will not be actually explained in this module because of the time of this module. But you are very welcome to look at this reference just to overview yourself about all these topologies. So I think that brings me to the end of this lecture. I hope you enjoyed, and I give you brief about the buck-boost converter and other topologies as a start and as a basics of power converters. Thank you very much, and see you in the coming videos.